finite element models will give you the best looking wrong answer you've ever seen. And I think AI will do the same thing for you if you're not careful.
Welcome to the Structural Engineering Podcast. We have an exciting one this week as we're talking about coding, a discussion on AI, and for industry as a whole to draw the talent we really need in keeping it. We have a few people joining us this week, so let them make their introductions.
My name is Connor Furster. I'm a design engineer at RJC Engineers, and I'm also the founder and lead instructor of Python for Structural Engineers at structuralpython.com. I am an open source author and maintainer. I have written the packages HandCalcs and For All People.
I'm Marianne Wachter. I'm a senior software engineer at a company called Outer Labs, and I've been contributing to open source since 2015. I have a couple of open source data visualization projects that I've worked on, and I also did a physics simulation open source project called Pymaxian.
My name is Craig Brink. I am a senior structural engineer working for Atkins Realis. Been practicing for about 16 years, primarily in the heavy steel, industrial, mining industry, and also in water and wastewater treatment plants, doing a lot of concrete masonry. I code as a hobby, learned Python probably 5 or 6 years ago, and have developed the project Pynite, which is a general finite element package for Python.
My name is Colin Caprani. I'm a professor in Monash University in Melbourne, Australia. Originally from Ireland. I've been a structural engineer since 1995 or something. But over the years, coding is the solution to a lot of things, and the open source system has really made it possible to get some good stuff out there. So I've authored PyCBA, continuous beam analysis package, OSP grillage, which is built on top of OpenC's for bridge deck grillage analysis, and Pystra, which is Python structural reliability analysis.
This episode is unusually hard to edit because since it's out of my traditional engineering practice, I have to Google everything they say. But to save you a little time, take a look at the show notes for many valuable links from the episode.
Well, thank you guys so much for joining us today. Max and I are really excited to talk about the topic of open source. We want to kind of start off with a question, and a lot of these questions are going to come from a basis of us knowing absolutely nothing. And that's what we're actually really excited about today, to understand from you all. As we just heard, there's so much experience here and from a structural perspective. But when we're kind of getting started, and the first thing kind of comes to mind is, what is open source engineering software and where can we find it?
Open source engineering software is basically software that is hosted on a public platform. Probably the most common one is GitHub, where a lot of people can go and download different packages in many different languages. So you can find it at github.com, which is owned by Microsoft. How does it typically work? Usually an open source software package will have a specific license in terms of how you can use it. Some of them are more restrictive, some of them are more open. But the idea is that you have access to the source code. You're able to see exactly how the software works, and you can use it for quite often your own personal use. There are some limitations with commercial use, but the idea is to create an ecosystem where people can build off of each other's software so that you don't have to basically start from scratch every time.
Regarding commercial use, Marianne's absolutely right. The commercial use can be restricted on open source. The word commercial use, though, can be ambiguous. Oftentimes it refers to when you want to sell copies of the software is often where the restriction is. When we're talking about commercial use, like with engineers working at a company employing the software for projects, those are often not restricted in open source licenses. But of course, as Marianne said, that they do vary. So being able to read the license and understand what your rights are is a very important part of the steps.
In open source, does that imply that there are multiple coders on a project? I guess, to help me define this open source, is it a one person can make a project and put it on a network that it makes it open source, or is it worked on by many people?
It depends on the project, really. Some projects have a few maintainers or even a single maintainer. Some projects have many, many maintainers. It really depends on the project you're looking at. On GitHub, when you're reviewing a project, you can see how many people are contributing to the project, what types of contributions they're making, how active they are, how recent they contributed. So it really depends on the project.
Okay.
The nice thing about open source, well, there's several nice things about the open source as a practice, and one of those is that as people find your project, they start using it. For example, with Craig's project, Pinite, as you discover it, you start reading about how to use it, you start trying it out, and you might quickly find that there's a key feature that you wish you had. That because Craig does structural engineering in the industrial sector, he may not, he's not even thinking about other people's needs. He's thinking of his own needs, which is the way to do it. And so you might find that, it'd be really nice if there was this particular feature. And so oftentimes contributors to projects come to be contributors by being users of the project, and then they think, it'd be nice to have this feature. And if they have a certain basic level of skill, especially because we're talking about engineering projects, and engineers all have that sort of technical ability to understand the nuts and bolts of how these calculations and analyses are to proceed, then they can go ahead and proactively contribute to the project by writing some code and suggesting it to the author to include in the project as a whole. And so this is one of the ways that new contributors come to new projects, and one of the ways that new features get added to it. And so the open source itself, the word doesn't necessarily imply multiple contributors, but because it is open source, it also implies an opportunity for other people to become contributors.
And one thing I would add to what Connor said is it's not just free reign on the code. There's a repository owner who controls what gets added or removed from the code. So if you want to make a suggestion, you would place what's called a pull request. Somebody reviews that and then decides, I want to include this, or maybe I want to edit this. And it just keeps undesirable stuff from getting in the code.
Right. So it kind of leads into the question of how, if people can contribute, how do you know that the code is any good? How do people know that the projects work? How do they know that they're correct and they give appropriate answers? And it's exactly as Craig said, is that the maintainer of the code gets to decide what gets put into it, right? So as a contributor, you're basically just offering suggestions. And to make the process of getting your feature included, you do as much work for the maintainer as possible so that they all have to just review it and basically click yes if they think it's really good work.
So what about on the side of stability? How stable are these programs if one were to download it or to utilize it? Do you usually find there's a lot of issues with it crashing, or really even maybe errors in what they've coded?
In the main, no. That's not to say that there can't be errors and bugs, but following on from the previous discussion, the version control workflow that software engineering has developed has emerged over many decades to address these problems. And so the formalism that's in place ensures that you have really good quality control of what comes out the other end. And in particular, for structural engineers, we might be concerned about the accuracy of calculations, especially when people are contributing. And we include in our packages something called testing. And testing is where we take a benchmark result and we make sure that the software is returning that benchmark result. And when somebody tries to contribute new code into our package, we run the proposed change against the benchmark to make sure that the proposed change does not break anything before the proposed change is actually incorporated into it. So for me, my experience of it is that the quality control on an open source project is often far superior to what we might see in terms of spreadsheets being emailed around the office, for example. We may come back to this topic, but it's really good. Look, and yes, there can be bugs, but sometimes those bugs emerge. They tend not to be mission critical bugs. They might just be usage bugs, or it doesn't plot quite right, or something like this. And those bugs then are often not in the main workflow of the package, because the main workflow of the package has usually been honed pretty well. And those bugs get ironed out by many, many eyes using and looking at this source code. So for me, it's more robust.
Adding on to that, I think in a lot of ways, the sort of testing paradigm that exists in open source is better than some of the stuff that you get in commercial software, because there are a lot of commercial software packages where the best that you'll get is kind of like a PDF with a bunch of examples, and it's kind of on you to sort of re-implement what's in the example and make sure that the results still match. I mean, commercial software often has bugs that, go unaddressed for a long time, or you're using the software in a different context than a very simple example that's in the sort of user manual. So I've found that the sort of testing workflow that is deeply embedded in software development now is usually a better path.
I find that in addition to tests, which I set up, and like Colin suggested, every time somebody issues a change, it automatically runs these tests and gives me an email saying, hey, these tests failed or these tests passed. In addition to that, I find even better than the tests I set up are hundreds, if not thousands of users worldwide emailing me from time to time saying, hey, this doesn't look right. And so I get free feedback from these users. And that's how I find the majority of my bugs. It's when users come back and say, hey, I've got an issue. There's an issue reporting procedure in GitHub. And when I see those, I tackle them fast.
In that way, these software packages end up being a lot more battle tested than some commercial tools, because the other thing is that when there's an issue, it's posted on a GitHub page and everyone can see what the issue is, right? So if you've got the same issue and you find it, you can go to the issues, you see the issue there. I mean, conversely, if you've got a commercial software package, you don't see them admitting their issues right on their website. So, I mean, we've had a scenario in our office where a software package that we've used for many years, they came out with a new version, and we ran a same test model on one, same test model on the other, and the deflection results were completely off. And so you would think that internally, surely this company, this large company whose job is to produce software that is going to work for the structural engineering market and for their clients, and that their reputation depends on it being correct, surely the minimum they would have done is run it against a simple model on two different versions. Yet that apparently did not happen. So the testing that we do in open source, because I don't know how to sort of separate or why these things happen, but I mean, we're all engineers contributing these projects, and maybe because of that engineering ethos, the reason that we do it, all these things behind it, we care deeply about it being correct, right? And so I would echo everyone else's that I actually have more faith in open source software than a lot of commercial software packages, because I have to be the one to go and discover all the flaws fresh every single time that I use a new software. Whereas in open source, it's been discovered, it's been talked about, we know kind of where the edges are. So it just gives me a lot more comfort.
I'd add to that there's a complete record of these conversations as well.
God, yes,
on online, right? And so you're new to a project, you're kind of keen to understand why the algorithm works the way the algorithm works, and you see some line in the code and you say, hey, where did that come from? And you can click on a thing that's called git blame, and you see, hey, this guy or girl changed it, back 3 years ago, and here's the conversation that they had when they went and changed it. Oh, and there's why. And by the way, they've linked on to a textbook that explains that algorithm in that line of code. Now, compare that to a closed source commercial offering. Gosh, I just, I'd echo Connor's comments. I mean, I tend to have, as they say, sunlight is a great disinfectant.
I've used a lot of commercial software packages over the years, and I don't want to say that they're bad. There's some things that they can do that I'll never have time to develop in my open source software. But I've been shocked at some of the bugs I've found after 16 years of practice that are just in very publicly used pieces of software. And sometimes I think we rely too much on our software to think for us. And that's part of my motivation for doing open source is I know the nuts and bolts of what the program is doing.
That I can really see the potential benefit. So for someone, how could engineers or new developers participate in open source engineering software?
Sort of the base. I mean, here's the thing is that a lot of these projects that we're talking about, Craig's project, Pinite, Colin's project, PyCBA, OSP Grillage, they all depend on the designer, the engineer, on having some facility with programming. And so the amount of programming skill they need to have is generally not very high, but it's not, these software packages don't have a graphical user interface or a GUI that commercial software packages have. They're meant to be interacted with on what's called the API, the application programming interface. So all these commercial software packages, beyond the GUIs, these graphical interfaces they have an API, which is what their graphical components interact with. Sometimes software packages expose these APIs, these commands behind the scenes to users to use. But when we're talking about open source projects, by and large, we're talking about these APIs that give designers access to them. So the difference would be that in a commercial package, you go click a menu, say file, new model, then you would click some parameters, and then you would sort of set a grid or set some material parameters through a series of menus. But when you're working with Pinite, Craig's project, you are going to be typing FE model 3D, and that creates your model. And then you're going to go say model.add nodes, and you define the coordinates of your nodes. Then you would say model.add members, and then say connected from this node to that node. So that's the process of it. And so it requires that sort of base level of programming skill to sort of start interacting with it. But like I said, often the projects that we're talking about here with this group of people, these are all in the Python programming language, which is designed from the beginning to be readable, to be understandable, and to be comprehensible, similar to just plain English.
Python code, I think, is easier to read than Excel spreadsheet type. If you can do Excel spreadsheets and read those formulas, your Python formulas can be much easier to understand.
I mean, one thing that I'd also point out is that what I've heard is that I think most introductory CS courses now are using Python rather than like I had my first programming course in Java. So Python is sort of the entry point for people to learn how to program in their engineering education. And as everyone else has said, there are a lot of benefits for that being Python. I think one of the other things that we've kind of seen a shift in the last 10 years is I think a lot of AEC programs, because they were often married to the Windows ecosystem, it meant that people were working in C#, which has a lot more overhead to learn than Python. But I think there's just been a lot more development within the Python ecosystem that's made contributing or understanding Python code a lot easier.
Just on Connor's point about the API and about the use of, a script may put some structural engineers off, but I'd like to kind of reassure them that actually there's a huge automation benefit. Because every time you click a mouse and drag a box and type on the keyboard, you're manually interacting with the computer. If you can imagine that you've got to set up, multiple very similar analyses, that's a lot of clicking and dragging, right? And automating that process and being able to only change one or two variables to produce the next concrete beam design or whatever it is, it's incredibly powerful. So don't see the lack of a GUI as a graphical user interface as problematic. See that as actually the benefit, the opportunity to script and interface and automate. And Michael Kennedy on his Python podcast, he talks about it being a superpower. So can you imagine being you, but like 10 times more powerful? Well, that's what the ability to script gives you, the ability to automate.
Some of the APIs that are available already have an interface for you. So a good example of that would be AutoCAD, right? You can script in AutoCAD with Python. You can script, I believe, in Revit with Python as well. You can script in Excel. You can use Python code to link to Excel, and I've used Excel as the interface for my Python code. I've linked Excel to Pinite. The more you get into it, the easier it is to kind of interface these already built interfaces with your code. And even if you're not using a pre-made API like that, there are some other projects out there like Jupyter, Spider. There's some programs already out there. Spider, for example, will give you a MATLAB-like interface. Jupyter gives you a notebook where you can put text and pictures and all kinds of things mixed in with your code. So there's ways to work around the scripting, and that shouldn't put you off.
I mean, one thing to add is that the barrier to entry has gotten even lower now because you can actually put Python code in Excel cells. So there's a direct integration that, like, as of, I think, a couple of weeks ago is possible.
Another thing is that ChatGPT can kick out Python code. You can ask it, hey, I want to do this. And ChatGPT can give you, it might not be 100% right, but it can give you the framework that gets you started and pointed the right direction.
Do you know how much all this costs? $0.
That's a good number.
You got to put this in perspective. It gives you the chance to be you, but like 10 times more efficient, productive at zero cost. And that's got to be a big one for small consultancies and so on. Yes, there's a learning curve. Yes, you're going to have to invest some time, but honestly, it's going to pay back dividends and productivity, over many, many years for sure.
To quickly interject, since you may be wondering this if you don't have the numbers handy, RAM Structural System advertises 12 months for $3,902. Just RAM Elements is $1,380, or ETABS for a bit more than $6,000 for the most basic. Even just in InterCalc for $1,545 per year. Not a comment on the value, just the numbers if you don't have them.
So a typical workflow for an engineer who has this little bit of scripting ability, they might be saying, okay, I've got to design this concrete beam that's going to be running through 5 bays. And so I can set up the parameters of what this is, all the spans, and then I need to do some kind of analysis based on a rotational stiffness of my columns. And so to be able to get the moment diagram of my beam as it goes across these 5 bays. And so they might think, okay, well, I need to do some sort of analysis now. Now, the bad idea is for you to say, oh, I got to program an analysis script myself. No. What you do is you start going onto GitHub, and you might run into Craig's project, you might run into Colin's project, PyCVA and Pinite. Then you start reading the documentation and say, this will do the analysis for me. What are the inputs that it needs? Okay, well, I've got this information here. I put the inputs there, and it gives me what in return? And it'll say, okay, well, this gives me a plot of my bending moment diagram across my bays, or it gives me the resulting arrays behind the plot, and so I can query what the moment is at any given location. So now that I've got that capability, now I might want to set up an automated design process. In order to do that, I've got my moment. I might now do a factoring process, and then I can start calculating my amount of steel required. So it's a process of sort of dependent on the designer at the moment in time that they're working with the problem that they have. And so these tools that we're talking about are kind of some of the things that you have available for free in this sort of global tool set of Python engineering tools. And so whether you use one for another project or another will depend on what you like and how you want to work and what the projects can give you in terms of the results that you're looking for.
We did a survey of our listeners and asked what topics do they want to hear about. And the one thing that kept coming up was 2 letters, AI. From the outside world, it seems like everything is changing when it comes to AI. I'm curious what your guys' opinions are about what that actually means and what that means to the structural engineering world, if you guys wouldn't mind.
Happy to talk on this. I gave a presentation on this. I mean, there's lots of interesting impacts. But the key thing is to know what AI is and how it works, and it's an enormous correlation engine, right? So it learns by looking at lots of examples of what's fed into it, and then it's able to reproduce and output patterns that it sees in those examples. If you're perhaps repeatedly designing very similar structures, then yes, AI could possibly be as good a designer as you, because it will have learned from the previous 20 portal frame buildings that you've designed, and it'll have a pretty good feel for in between the two extremes. It's an interpolator, not an extrapolator, right? But in between the domain that you've already worked in, it'll have a pretty good estimate. Do I think we should be worried? Look, I believe wholeheartedly in our profession, and I believe that we offer and have an enormous creative input into the building and structure that we see around us. I think that we should not be afraid, because we should be creating really smart solutions to the problems that are in front of us. And with the changing paradigm in terms of sustainability that we need to be incorporating into structural engineering, AI is not going to have a database to learn from, because we haven't yet built those buildings that are solving net zero for the 21st century. So I think we have a lot of creativity ahead of us. And so I'm not too concerned, to be honest. I think some people may be displaced, but overall, I think our profession is at the forefront of solving the next set of problems.
So regarding AI, I remember a few years ago, it's probably around 2018, 2019, there's this talk of self-driving cars, right? And it was seemed to be taking off and doing really well. And then we had a few car accidents that were really bad, and none of the car producers want to take ownership of that, right? And so now they tell you got to have your hands on the wheel, even if it's a self-driving car. I think that's the same thing with engineering, is structural engineering. The buck has to stop with somebody. Microsoft is not going to come in and say, hey, we'll take responsibility for all this structural engineering. And as long as they need somebody responsible, they're going to need an engineer to validate what AI is producing. And they're going to need somebody to take responsibility for that structure. And that person is going to have to still have a structural engineering knowledge. So I see it as enhancing our profession. I think it's a positive thing. I use it all the time these days to help build out Pinite even faster than I've ever built it before. But everything that it kicks out, I have to validate myself.
I think one of the things probably everyone on this podcast has heard from a professor at some point is garbage in, garbage out. And one of the biggest challenges I think I've seen within structural engineering is just data quality. And it's like, if you go to ChatGPT right now and try to get it to give you the results for designing a standard beam, it would probably get it wrong. I guess for better or for worse, there isn't a lot of open data about how we design our buildings out there. I think that's just the nature of the industry. What I have seen in terms of people trying to, or feeding better data sets to AI models for structural engineering, it's basically, running a bunch of parametric models to generate synthetic data and then use that to extrapolate, as Colin said, the expected behavior. So there is a place for it, but in terms of a lot of the sort of embedded engineering knowledge, it's not like, traditional software engineering. A lot of these models were trained on scraping significant code bases. And, that sort of structural engineering knowledge just isn't really out there anywhere. So given the sort of closed nature of the industry, which is something that I don't necessarily think is great, it seems very unlikely that this will be something that will completely replace what structural engineers do. And the other aspect is, I think Colin brought this up a little bit, in terms of sustainability, we're going to have to change how we design buildings. And I think a lot of what we're going to have to do is think about how we reuse the buildings that we have. And that's just not something that you can really do without being a human and like walking the site and trying to figure out like what already exists. So I think in terms of like what the future of the structural engineering profession is going to have to be, it's not something that is going to be easily sort of fed to an AI model.
My first engineering mentor is a guy named Robin. And it was my first design summer job. He called me into his office at one point and he said, Connor, like, what is it that we get paid to do? And I naively was like, well, to tell our clients that their building is safe, or to design a safe building for our clients. And he looked at me, he said, wrong. He said, our job is to ask the questions our clients haven't thought to ask yet. So when we're talking about AI, and I'm going to, sort of say finite element modeling and then say calculators, is that when pocket calculators came out, there was a big hubbub about it. There was college professors being like, we shouldn't use these. And then there's this great quote from Picasso, the painter, that's saying, I don't know why everyone's so excited about calculators. All they give you is answers. And so, and I'm going to group finite element into the same topic, is that finite element is not sort of like the panacea to like all structural problems. All it gives you is answers for a problem that you define. It doesn't tell you what questions to ask. And so as a result, it doesn't really do any engineering work. The AI large language models that I think is sort of captured everyone's imagination, they are going to give you an answer no matter what. They're going to tell you basically what you want to hear. And you're going to prompt it to tell you what you want to have back. And so to look for these kinds of tools for insight is, I think, a flawed, imperfect approach. There might be scenarios where insight might be possible, but it's not because the technology itself is giving you the insight. It's because somebody has trained it on another perspective that you haven't seen before. And so it's regurgitating that to you now. And so they might be a nice introductory tool, kind of like how Wikipedia is a great introductory tool for research, but it's not where you end your research. It's just sort of a launching pad. So for large language models that are generating output for you, they can be a really great place to start and get an orientation onto something, learn a few tricks in Python, ask it for a few specific pointers on how to use a certain library that it might have been trained on. But then the other kinds of AI, and again, this is a term that's being sort of used to group a wide range of technologies that are quite different, is that is a sort of classification problems. I have my stepbrother called me up and he was saying he was concerned about AI. He's a mechanical engineer, and he was saying that, I'm kind of worried about AI and machine learning sort of affecting my job. And I said, well, how do you mean? I said, because that's really just for solving classification problems. I don't really do classification problems in my job all day. And he said, well, actually, that's exactly what we do. We do classification problems. And so in his case is regarding pipeline integrity, right? So you send an instrument tool all the way down, it gives you a whole bunch of data, then you classify the data based on the patterns that you're seeing, which is exactly a classification problem. So I think that there's, in this lump of technologies that we're ascribing the label AI to, there are some technologies that I think can have an impact in the structural world. One of those, I think, is in structural health monitoring. I was reading in an email recently that someone's point of view is that AI is, at its core, a surveillance technology. And so now they're referring to it in terms of people, and I think that it's a true statement. But what do we do as that surveillance in structural engineering is we look at assets and we look at bridges and we look at how these things are maintained. So in that perspective of AI as a surveillance-based technology, there are some, I think, small areas of the field where these can certainly assist. But to sort of look at it as, I've heard young engineers say this exact phrase, in structural engineering, experience doesn't matter anymore now that we have this kind of technology. And so it's not to sort of say that everyone's grouped in the same way, but I think there's a lot of, is overestimating the potential of the technology, I think. And it creates illusions of a future that is not necessarily the future that is going to be an outcome of this technology. So I think that it has potential in certain limited applications, but at the end of the day, you have a computer in front of you. That computer can do anything you want it to. as long as you know how to operate it. Now, back in sort of the mid and sort of late 20th century, being a computer operator meant you knew how to program the computer. Nowadays, we use applications. And now we've lost that ability to make the computer do what we want, how to operate the computer. Instead, we just operate applications. And so I think that part of this drive for developing open source engineering software is that we are now developing tools that we want to have. And I think that engineering being a very human-centered activity can be even better as a human-centered activity. But if we create tools that remove the human from it, then it sort of is in conflict. But we can instead create software engineering tools that enhance the use of the human being and enhances the humanity of the process. And in my language, I like to say it just can make engineering a lot more fun. So I think that one of the motivations for creating all these tools that we do is to enhance and make it more fun to do engineering. Because when you're using commercial tools, you're locked into that process. But if the process isn't one you like, or is very uncomfortable for you, or doesn't work how you want, then you now have the ability to create a process or tools that are more aligned with how you want to practice.
One more thought I had about AI is if you go back and look at what finite element modeling has done for us, I like to tell younger engineers or new engineers that I'm training, finite element models will give you the best looking wrong answer you've ever seen. And I think AI will do the same thing for you if you're not careful.
All right, Craig, this one I want you to start this one. So how do you use open source engineering software to do production within the engineering that you do day to day?
Yeah. So I'll usually identify a repetitive task that drives me bonkers, that I hate doing. And once I find that task, that is prime for optimization for programming. So I often find pieces of software. I wish a piece of software just did something a little bit differently, or I find an error in a piece of software that maybe the software overstates what it does. And like, nah, it doesn't account for this or that. That's usually where I need a custom tool, and I'll build it out. And, when I first started this, my tools were pretty simple and pretty basic. Now, as I've gotten into it more and more, these tools are building up on top of each other, and they're getting more and more advanced. I'm getting faster at what I do. So I would say, how do I implement it? I identify a problem, and I automate it, and I just keep adding pieces and parts. And pretty soon I've got a tool where other people in the office might be looking, hey, how'd you do that? How'd you do that so quick or so easily?
To follow that up, how does jurisdictions what does it look like when you submit your calculations from an open source standpoint, right? They're so used to seeing kind of more of the commercially available software being submitted. Are you submitting pages of code?
So no, in fact, I have to basically clean it out as I present it generally. And maybe other people are different, but a good library for that, for example, is Connor's HandCalcs. It can take your computer code and convert it into pretty looking formatted equations, almost like what's the program, MathCAD, very similar. So I usually run it through that, or I'll have a front on my program like Excel, where I format the output on Excel, and then I run my code in the background and it populates Excel for me. Jupyter Lab is another one that can kind of format it in pretty ways. If you're familiar with another package called Jinja, I'll use Jinja sometimes, Jinja 2, sorry, and it will format it really nicely for you in just about any way you can dream.
I've been, as much as if you asked me a couple of years ago if I would ever come around to this, I would have said, heck no. But I've been coming around to realizing that Microsoft Word documents can be an incredibly simple and effective way of producing reports in Python. And because they're editable, right? So you can set up a set of styles just within Microsoft's Word. Then you can just dump some data into it, but you can dump the data into it in a nice sort of pre-formatted way, and you can style it to look fantastic. And something that I've included in my course sort of midway through now is that this ability for people to design their own output reports from taking analysis data from Pinite and putting it into an analysis report that they design themselves for their own purposes using Microsoft Word. So it feels like, oh, there's this API, you're programming, getting this output, but where do you put the output? Do you just like send your computer code? No, of course not. No, it's the part of the decision, of course, as I think an engineer, after you've done the analysis, after you've done the design, is now communicating that and all the decisions you've done, right? So to output computer code, I think it would be a bad idea. But you can use computer code to output beautiful looking reports in a way that's automated as well. So it's you set up templates and then you populate the data.
Yeah, one thing that kind of hasn't been touched on, but something that I did a lot as a structural engineer was using open source software for converting models from different platforms to other platforms. So I used the BOM and contributed to the BOM when I was a structural engineer at Bureau Happold. And so that's an open source project that basically will allow you to interface between your ETABS model and your Revit model and like automatically get the geometry out and share models in between different pieces of software, commercial and open source. And there's also another open source engineering software out there called Speckle, where you can do something similar with, instead of, we've been talking a lot about like calculations, but this is at the model level of being able to validate your model, like check changes in your model, see like a version history of like what's changed in your model over time. And, there are a number of open source options for doing that now.
I guess my use as an academic is going to be a little bit different, but maybe just two examples. I sit on the code committee for the Australian Bridge Standard, and recently we were going through an amendment, and I looked into the origins of this one little number in terms of the allowable torsional rigidity in a bridge deck, and it had emerged from one guy sitting down with a graphical user interface. And he had done, I think it was 3 or 4 bridge deck analyses. Now, that's a lot of work, right? You're doing that manually, inputting all that information. And in the space of about half a day, I had automated an analysis, and we did 110 bridge decks in that time, simply leaning on those tools. And I was able to output some information that convinced the code committee that actually, no, we can change this number a little bit. So the scalability is significant. The second example, and I'm still at the heck no phase, Connor. I'm still not going to come back around to the word just yet, but I do use LaTeX quite a bit, and I can interface code with LaTeX really nicely to output really beautiful reports and so on. And I'm probably going to step further in that I generate quizzes for my students and generate like lots of variabilities in those quizzes and try and make the questions creative. A lot of them are images, and I use another open source package, but it's not Python. It's in LaTeX. It's called Stanley, and it produces beautiful drawings of structures and loadings and so on. But I've been able to automate all of those drawings. So I'm able to generate, a beam that's, 9 meters long and has this UDL on it and lots of variabilities. I'm able to do the analysis automatically. I'm able to produce the outputs, for example, influence lines, which is one of the motivators for me for PyCBA. And then I'm able to automatically pull that into a LaTeX document that gets compiled into HTML of all things, and then gets uploaded into the learning management system for the university and becomes a quiz that students take. That entire workflow is automated. I don't need to click buttons. The only place I do need to click things is in our learning management system. If I want to make a change across 200 or 300 students, of course, it's a graphical user interface, and I get repetitive strain injury trying to do this. And so again, I lean on tools like Selenium, which is it's called a web driver. And you can program Selenium to do the clicking for you. So you say, hey, go to this button, click, wait 2 seconds for the page to load, click, now go over here and check that this form has this correct number in there, click. And I automate that, again, to drive my interfacing with the computer. The computer is not in control. I'm in control.
So there's been a lot of talk about how you work through projects with code you've written yourself and you really understand the problem you're getting at. Do you guys think there might be problems with the way structural engineering is currently practiced, and what do you think those problems are?
I got to preface this by saying that my practice time is from quite a while ago. I know the industry has changed, but I do see a lot still of spreadsheet use. I find conversations like we had about the threat of AI to engineering is at a different level to where a lot of engineering is practiced, which is the manipulation of spreadsheets. To me, they are orders of magnitude separated in terms of their technological depth. Spreadsheets, there's quite a lot of research been done on the errors in spreadsheets. And this is not particular to structural engineering, but it's one guy, this guy Panko, has done quite a bit of work, and 90% of spreadsheets have errors. And worse than that is that each cell, you've got about a 1% chance of having an error in a cell. And of course, these errors in cells cascade. Excel or any spreadsheet, I don't want to pick on Excel too much, but it facilitates errors. It's horrendously bad at preventing you from making errors. And the code that's in cells is a type of coding known as go-to statements. We got rid of them in the 70s in software engineering because we recognized it leads to what's called spaghetti code. Things interact with things you never intended to interact with things. So all in all, it's a very useful tool for producing tables for business reports, but I think we've been pushing it beyond its intended limits and running into a lot of problems as a result. There's a huge number of failures caused by spreadsheet, not structural failures, I should say, business failures. Lots of even choices made around the COVID response in the UK were driven off spreadsheets, and there was an error there that they reckon cost many, many lives. We have to be really, really careful about using spreadsheets because they're not version controlled. They're often lost to the mist of time as to who developed them and where they were developed from. And I think what we outlined at the start in terms of the robustness of the open source ecosystem, it contrasts hugely with maybe where current practice is in terms of the use of spreadsheets. I'm trying to be measured here because this is a topic that gets me incredibly impassioned because, I think we can do better as a profession than say, yeah, I drive spreadsheets every day. That's what I do. That's, we can do better, and the tools are out there for us to do better.
For the motivated, Colin has produced a half-hour presentation on this exact topic on YouTube. It's excellent, and you don't have to search very hard to find it.
It's called Excel is Evil.
That's the one.
That'll be linked down in the show notes as well.
Look, that presentation is really around research because that was a low-hanging fruit. But my concern does drive into the profession. But I've found that conversations with practicing structural engineers become mired in a dogmatic stance. I've found that people are not willing to be challenged on their use of spreadsheets, which to me, perhaps the sensitivity that is exhibited there perhaps points to a deeper truth that they recognize that it's not the right tool for a lot of what we use it for.
Just going off of that, I've seen frequently on Reddit that's come up in the structural engineering subforum of people defending spreadsheets to the death. And I've even seen people say they say that a spreadsheet is more transparent than Python, which I have a really hard time with. But yeah, I think one of the biggest sort of challenges to get around with how engineering is practiced, and I think something that probably everyone has experienced, is that there's this mentality of, you have to build the spreadsheet, you have to start from scratch. And while I understand like the reasoning behind that, because then it's like, well, you own what's in the spreadsheet, just with the way that projects are done these days, everybody passes around spreadsheets in the office. And, sometimes you'll be lucky and there will be some kind of vetting process. But like, as Colin said, every spreadsheet has errors. And it's just like whether you're going to catch them or not. Yeah. And the other thing that I particularly have an issue with within structural engineering is like, okay, Excel is one thing. You can click into a cell and see what the formulas are and like go through it. I think structural engineering education really likes to say, we have to solve everything from scratch. We take like a matrix structural analysis class to understand like how the commercial software that we use works. But then when we are using the commercial software, it's a black box. If you're really, really lucky, you'll have enough time to do mesh sensitivity studies to make sure that you aren't just getting garbage out of something. But a lot of the times, at least with some of the projects that I worked on, we were really pushing commercial software to its limits. And, then we got in this situation where it's like, okay, well, now we have to use two different sets of commercial software to make sure that they match each other. And when I hear people say that they don't want to use open source software because, there might be errors, and it's like, there's no difference in the commercial software that you're using. It's just like you won't be able to actually dig into the code and see exactly what's going on. And that's something that I particularly like about writing software is it's like you are able to really dig into it.
So I agree. I think we delegate too much of our engineering know-how to computer programs in general. And I think that goes for open source as well as commercial software. I think we shouldn't expect our software to be smarter than we are. And that's where we really get into trouble. An engineer is really needed with a brain on every project. We take these hard classes for a reason. It doesn't mean you have to solve every problem the hard way. That's why we have these tools. But you should be able to look at a piece of software and the output it's producing and come up with a quick hand calc that either validates it or invalidates it. And I think that is the biggest problem I'm seeing is that we've got this magical software, this black box that solves the world's problems in an instant. And one of my fears with putting Pinite out there is that it will get used that way. And there's a big disclaimer in my software that says there's no guarantees this is doing it right. I think it is. I try to keep it as clean as possible. I got a lot of eyes on it, but ultimately every piece of software you use has that disclaimer that says we're not taking liability.
I think one of the things that draws me towards the open source sort of ethos and community is that it's about sharing information. We talked about before that when there is an issue with an open source tool, you see it on the issues if someone's reported it, and you can see discussions about it, and it's all there in the open for you to understand. Conversely, the example I said is that, our office discovered, a commercial package that we use and it has this error, and I'm not going to be telling you which ones, right? Because professionally, I don't think that's the way to do it. But now that means that all those other engineers out there are probably using the same software, they don't have that knowledge, right? And that's also part of our company paid for it internally. So that's our knowledge now. And so it's really, I think the open source ethos of this sharing of engineering knowledge, I think just benefits the engineering community so greatly, and especially when in contrasted to our sort of siloed internal company knowledge. When you work at a company that's been around for many decades, then they've developed that sort of internal knowledge base, which is very valuable. And as an engineer who works at a company like that, you get the privilege of accessing it. But what about the community at large? Then I think that the open source engineering community is a place where that sort of knowledge can be built and shared in the open, and that sort of benefit to be distributed amongst all practicing engineers around the world. When it comes to tools, no matter what tools you use, they will own you. And so whether that's a pencil and paper, for example, I have a hard time getting ideas out of my head unless I draw them or write them. And that's an example of the pencil being a tool that I'm now reliant on. The open source engineering tools that I develop, my hand calc software, you just type the formula and it renders it out with the numeric substitution. I had an instructor at my alma mater, SAIT Polytechnic, and he told us, calculators make you stupid. And that was the first time I had a programming calculator, and I thought it would be really clever to program in a whole bunch of my water resources equations into there so I could get through my exams quickly. And sure enough, after I spent hours, typing those little programs into the calculator, I got through my exam quickly. But can I remember how to do that stuff now? No, because I offloaded that memory and that technology and that learning into a calculator. So with my own tool, HandCalcs, I've been telling myself more recently that I want to build engineering software that enhances the understanding of the engineer. And I don't want to be building software that diminishes engineering understanding. And so with HandCalcs, I'm on the fence. I don't know. I'm neutral about it. Is it diminishing understanding or is it enhancing? I don't know yet. And so just like Craig said, even the tool that he built himself, Pinite, you question whether or not the things that you've built are going to be contributing to sort of a dehumanization of the profession. So I think these questions that we ask, especially when you build any kind of tool, is really important, especially if you're building tools internally in a company. I think that when you build tools internally for a company, to make a tool that just sort of you export some results and then it does all the calculations and creates a design and puts it directly into Revit is maybe not a way of enhancing engineering understanding within your organization. And so these are the questions that any tool building you do are going to be important ones to ask for the start of any kind of tool building project or through the development of your career. So as far as open source goes, I appreciate that it's open and I appreciate that it's everything is talked about and everything is known. But at the same time, just because it's open source doesn't mean it's positively contributing.
And something that Connor prompted there in my mind, and we haven't touched on yet, is I see open source as de-risking our designs for the future. When you're storing information in a plain text format, and scripting is plain text, all I need to go along with my plain text is the packages, and they can be siloed in what are called virtual environments. So I can take my script and I can take the packages that ran that script and I can put them in a zip file and I can archive them. Right. And so in 20 years time, I can come back and rerun that and it will give me the same results as I did today. And I am concerned that when we tie ourselves tightly to a commercial provider, we are very much subject to their whims and to the market forces that they're subject to. And I have seen repeatedly cases where we are digging up old designs and the software is no longer available. The software can't be installed. We cannot check or reproduce how we got those results. So for me, this added benefit of open source is its future-proofing, its robustness to the whims of others that could otherwise impact on my ability to deliver services to my clients 10, 20 years into the future.
That's a really good point.
Yeah.
Yeah, I started out my career as a bridge engineer, and one of the sort of interesting transitions that I saw was that for long span bridges, the commercial software didn't exist. So every single bridge company wrote their own software to design these long span bridges. And there was this kind of transition away from being able to use in-house software to having to use commercial software, which I think was just a giant mistake, because it's like these, as we've been talking about with open source, I mean, this was internal to companies, but it's like their software was battle tested and they had the source code. And I can't tell you the number of times that I did have to work on projects where we would have to dig up old models. And it was like, even a model that was 2 years old, couldn't be opened. And then it was like, oh, well, you're going to have to go back and maybe try to get the old version of the software to get it to open again. So there's just there definitely is a lot of concern about this historical context and losing the ability to understand the engineering that's already been done.
I think that's just so hugely important, because we keep these engineering records, right, of the designs, right? And it's when something bad happens, unfortunate happens, that now this is going to get dug up. And if it's because the commercial software is now going on to these like yearly subscription models, and then their old versions are out of date very quickly, and you will not be able to access them again or open up your old model. Maybe the software company will assist you in sort of transferring it into the new version, but they have no obligation to. It's the ability to silo and zip everything up into an archive and to be able to rerun everything. I think it's just, it can't be overstated how important that could be.
Well, with that, I'd like to go around and discuss each one of your guys' kind of final thoughts you'd like to share on open sourcing software.
I want to pick on Marianne because you've traveled a path that we see, Marianne, so many people now leaving structural engineering. And Zach, I mean, is that a topic that you want to touch on? But we want to keep the best young people and the best people and people like Marianne who have such skill sets and are going to bring structural engineering to the next level. They're leaving. And I'd like to talk about that if we can. And I think it interfaces with the open source, right?
Oh, absolutely. I think it'd be wonderful.
I would be very curious. And what was the incentive to leave? Like, did you see something in a different path that really drew you in, or were you seeing that you weren't loving the structural aspect? Were you repelled, or were you drawn to something, I guess?
So it was a little bit of both. I think one of the things that I had always sort of sought out in my career was a more technical path. And where I had seen different companies, that sort of like technical specialists track just didn't really exist anymore. It was, and I don't know if that's part of the economic forces of like the recession and then the pandemic of, an emphasis on work winners. I had wanted to be writing software since about 2015. And like where I saw my career going was still getting pushed into just project management. I really, and I think one of the things that is sort of missing from the structural engineering industry is this kind of software development. Like usually when you see someone in a structural engineering firm that's doing software development, it's pretty limited and they're very siloed. For where I wanted my career to go, I really wanted to be building software on a team. And that just didn't really seem to be an option within traditional structural engineering practice. Yeah.
Well, thank you for sharing that with us. And Colin, thanks for bringing that up. Appreciate that. Yeah. I think Max and I get a lot of emails about this too. And there's a lot of people out there that want to be more technical and more driven. And they feel that they're just driven into these management roles so quickly. And that, they really want to stay within the engineering side of things. And I think it is something we really need to push as an industry to keep fostering and really keep that position as a thing. It's mind-boggling to even think of or even to say out loud that we're becoming less technical or pushing less technical aspects of our job as engineers. Yeah.
Fully agree, Zach. And the challenges that we're facing now are going to require ever more technical solutions. And this is coming at a time when, as this conversation has shown, that I guess bluntly, we're tending to dumb down the practice of structural engineering, perhaps because that's a productive or more profitable way of doing it. This panel and others beyond it, I guess, we are people who look at those technical things and we want to get into the nuts and bolts of how things work and code it up and get it out there and have conversations about it. I guess it's a reaction perhaps to that, to keep it technical, to deepen the technical expertise in the profession, because we're really going to need it. We're really going to need people to be able to put wind turbines on the tops of existing buildings, for example, crazy things that we haven't thought about yet. But if we only ever see the world through, spreadsheets, are we really ready to tackle those kind of problems? And we have to deepen and expand our technical competence as a profession.
Yeah. I don't even know where to go from there, man. As we're kind of wrapping up here with our time, I just want to, I guess, kind of end us here with a kind of an open question for each one of you, and to go around what your final thoughts would be that you'd like to share on open source, and then maybe some tips to some engineers that might want to do that, or any maybe career advice to any of the young engineers that listen to our podcast. And Greg, if it's okay with you, we'll start with you.
Yeah, I would say, first off, it's easier than you think to get started. It's, like I said, I picked up Python probably 5 years ago, and I'm just, I had some prior coding background, but it's easy to do. Python makes it easy. AI has made it easy to coach you as you go and help get over some of the hurdles that I had to go through. I would also say that it is a great way to learn. Part of the reason I've done Pynite is just to learn what my software is doing on my own. I can go into a computer, commercial program now, and have a really good idea of what assumptions it's making, what it's not doing for me that I did think it was doing for me before I coded. So as far as a learning opportunity, it's the best there is. I think you different levels of learning. One of the higher levels of learning is being able to teach something to somebody else, right? To teach something to a computer, it's the dumbest student you'll ever teach, and so you have to know it really well.
Colin, how about yourself?
It's very hard to follow that. Look, I try and get my students operating in this space and I've over many years kind of moved around lots of different systems, but I've come onto the open source Python kind of ecosystem as being really the right compromise between lots of different things, cost free, and as long as you're able to just use the Microsoft Store, you can install it on a Microsoft PC. You don't need admin rights. If you're on Linux or Mac, it's already there. So just get started. Don't hesitate. If you're using Excel, you've already got the right kind of mindset for if statements, go-to statements. You're already scripting, so just go to the right environment and script. And over time, you'll begin to see that your productivity is increased hugely, and soon enough, you'll be able to produce things that other people who've not taken this path can't produce. So it's highly, highly encouraged. I think from a professional point of view, from the overall profession's point of view, I think it's where we have to go. I think we have to be upskilling our game as we move forward to these enormous challenges that are in front of us.
Thank you. Marianne?
Yeah, I think one of the sort of best aspects of working in open source and contributing to open source is just being able to meet other people like through that community that you wouldn't normally encounter. I think structural engineers tend to be kind of siloed in their professional networks a bit, and contributing to open source or using open source is like a great way to meet other people around the world who are doing engineering in different ways. I definitely think that working in software, or like my path to being a software engineer from a structural engineer, writing software made me a better structural engineer. It made me more systematic. It made me like, you have to have this understanding of every single step that you need to take. And, that lends itself very much to, how we design buildings. But yeah, I think one of the things that we didn't necessarily talk as much about is the community that exists in open source, and the kind of people that want to contribute to open source usually are the kind of people that want feedback. They want to hear your questions. I think the community aspect of it is like one of the most valuable things about open source.
Awesome. Thank you. And Connor?
Yeah, exactly what Marianne said. I mean, the fact that this is a panel, not one person, is sort of testament to that, right? And I'm going to say two things. One is that as I think we all go into engineering because we want to build cool stuff and make cool stuff, right? And when you start your career as an engineer, you're not the person deciding what cool stuff gets to get made or get done. And so that creativity part of engineering that I think a lot of young engineers are drawn to engineering for can often not be expressed early on. I find that contributing to and writing my own structural engineering software, putting them out into the open source ecosystem, is an incredibly fulfilling outlet for that creativity and has made engineering just so much more fun than it would be for me without that outlet. The second thing I'd like to say is if you are an engineer who is interested in learning how to use these open source tools, Pinite by Craig and PyCBA by Colin, in addition to others, my course Python for Structural Engineers is designed for engineers doing practical, daily deriving kind of structural engineering projects and how to integrate these kinds of tools into your practice.
Awesome. Well, thank you guys all so much for being on the podcast today. We're really excited to share this knowledge with all of our listeners, and we really do hope that maybe we can get you guys back on here soon to talk more about open source and really share more knowledge. That's a big thing that Max and I, the main reason we have the podcast is to share as much knowledge as we can and really bring the engineering community together. So thank you, all of you.
Thank you.
Thanks.
Thank you.